Welcome grade 10s to our 14th session, can you believe it? And today we are looking at mechanical energy. This obviously comes after the section of mechanics. You would have dealt with your vectors, you've now done work, energy and power, and now we specifically need to look at mechanical energy. It's a really important section. You've done energy before, so let's just quickly look at what I'm going to be covering in today's lesson, all right? So what we're going to do is we're going to focus on potential energy. We're going to do the definition. We're going to look at the equation, how to calculate it. We're going to look at kinetic energy, how to calculate it, what is its definition. And then we're going to introduce a new concept called mechanical energy, and this is a very important concept. You're going to deal with it a lot. And then we're going to, and within that, we're going to do conservation of mechanical energy. Conservation of mechanical energy is very important in grade 10s. We actually base a lot of our physics principles based on this, and you're going to see it again when you go to grade 12, when you look at momentum and all of that sort of stuff, and a little bit of momentum next year. So that's really, really important. So let's jump right in there. We're going to go to potential energy. I'm hoping some of you remember this from grade 9. Now, potential energy is the object and has is the energy an object has due to its position. Specifically for us in grade 10, we're looking at its position in a gravitational field. Okay, now you've got to get this. We can have electrical potential because an object sits in an electric field. Okay, we can have magnetic potential is not a great example, but we can have magnetic potential because two magnetic objects are in the same field. So when we talk about the field, we're talking about something that exerts a force on the object. Now we're very specifically looking at gravitational potential energy, and throughout your syllabus, whenever they just refer to potential energy, they mean gravitational potential energy. So it's the energy I have because I'm in a gravitational field, and it's the potential for something to happen. Okay, now what that means is if we look at the equation, and grade 10s, if you look at past books, especially over the last couple of years, you'll see that EP is sometimes written as a U. That's fine. They have decided to go back to EP, and EP stands for potential energy. Okay? And I'm hoping you all remember from grade 9 that energy is measured in joules. Okay? M is mass, because we're looking at an object, whatever that object will be, and that is measured in kilograms. G, now this is an important one, is acceleration due to gravity, and I'm using gravity because I'm in a gravitational field. And I'm hoping you also all remember that acceleration due to gravity is very specific in that it is 9.8 meters per second squared. And then the last one is h, which is height. And that is measured in meters. So what I mean is if I look at my pen, for example, I take my pen and it's now in the air. It has a height in relation to a couple of things. One, there's a height in relation to the desk, okay, which gives it a specific amount of potential relative to the desk, but it also has a height due to the floor, which you can't see, so there's another gravitational potential energy, but, okay, it also has a height relative to the ground, to the earth below. Now, we're on the second floor of a building, so that's actually quite high if I had to go right down to ground level. So this potential energy depends on where I measure it from. So that height isn't necessarily from the surface of the earth. It's relative to what we call our reference point, which you have done, and that's our 0 point. Okay, so what are we measuring it from? Okay, it doesn't have to be moving when it has potential, but it means with my pen in the air, I can drop it, I can throw it up, I have the potential for something to happen. Potential energy, okay? Nothing might be happening, but it has the potential to do something, and then we're going to look at what happens when it changes, okay? So we're going to get right in here because a lot of this is revision from grade 9, is we're going to jump into an example, and I've got an example here that says a boy of mass 30 kilograms, mass 30 kilograms, climbs onto the roof of a garage. Only boys would do something like that. And the roof is 2.5 meters from the ground. They ask you, how much potential energy did the boy gain by climbing on the roof? So if we draw it as a diagram, there's my garage, which we said is 2.5 meters high. And the boy climbs up onto the roof, and he has a mass of 30. Okay, so he's a very small boy. Okay, he climbs onto the roof. He's gained potential because he's gone from a position, when we look at him at the bottom over here, he has 0 potential energy because he's on the ground. There's no height. Anything times by 0 is 0, okay? He now climbs up the roof, and by climbing up the roof, he gains potential energy, and that's what they're asking you to calculate. So we go back to the equation and we say, well, potential energy is mass times gravity times height, and we go, well, this is actually quite nice because we know that mass is 30, gravity is 9.8, height is 2.5, and we go, okay, well, we take out our calculators, we put it in, and I've already done that, okay, and we get 735 joules. It's not a lot, but it's a relatively easy amount. Now, we're going to look at a little bit later on today in this lesson, is we're going to look at what we can do with that potential, okay? We're going to see how it changes into something else, because that's actually quite important for us. Okay, you ready for another example? Excellent. Now, still part of the same question. The boy now jumps down. What is his potential energy 1 meter from the ground? So back to the drawing. This was the original situation. And he had a mass of 30 kilograms. Now they say to you, he jumps off the roof. He jumps off. And they ask you, if he's now 1 meter here, above the ground, so at this position, what is his potential energy? Grade 10s, what you need to realize is I'm not asking you what happens to energy, okay? I'm not asking you where it goes or anything to that effect. I'm just saying to you that he jumps off, and now I want to know the potential energy 1 meter above the ground. His mass hasn't changed. That's not going to change. Acceleration due to gravity isn't going to change. What has changed, so that should be a 2, what has changed is his height. That's only 1 meter now, not 2.5. You all following me, I hope? We have all of that information, which means if I now want to find EP, potential energy, we go 30 times 9.8 times 1, and we get 294 joules. I'm hoping some of you now are going, hang on, wait, Tracy. At the beginning, we had 735, so over here, he has 735 joules of potential energy. Now he's only got 294 joules of potential energy. What happened to that energy? Where did it go? Good question, because if you stay tuned, I'm going to answer that for you. That's a very important thing to be thinking of, because I'm hoping as well that you remember, because you've done this grade 8, grade 9, you learned the law of conservation of energy that says energy cannot be created or destroyed. So if I'm now going, okay, he had 735, now he only has 294. Where did the rest go? We need to figure that out, okay? And we're going to get back to that, so hang tight. Second one. Now, the third part of this question, is what is the potential energy of the boy when he lands on the ground? Same situation, okay? But he lands on the ground, so his height is now 0. So we can work this out. Potential energy, mass, times gravity, times height. You're going to know this equation backwards by the time you're finished. 30 times 9.8 times 0, and you all know that 0 times anything is 0, okay? Why is potential energy 0? Because the reference point, which is the ground, and him, there's no difference in height. He no longer has a position as such in the gravitational field. They're all at 0, okay? So be careful there, because that's a bit of a tricky one, but it's 0 now. So, next type of energy you're going to look at is kinetic, EK. Some of you might see in the older books, EK is also sometimes written as a K. We're now using EK for kinetic energy. And it's the energy an object has due to its motion. An object must be moving to have kinetic energy. So when you watch me teach, and you see that if I had to tie my hands behind my back, I would not be able to speak. My hands have lots of kinetic energy while I'm teaching. My pen, when I hold it at here, has potential energy. It's not moving, doesn't have kinetic energy. It's stationary, does not have a velocity or a speed, okay? I let it drop, now it has kinetic energy. So if I let it drop, it gets kinetic energy because it's moving. Quick thing while I remember, energy is a scalar, grade 10s. Scalar means we don't consider direction. So we don't get positive and negative energy in grade 10. You're going to look at positive and negative work when you get to grade 12, but no positive and negative energy because it's a scalar, has no direction, so we don't care about the direction it's moving in. So when I consider my pen, whether I'm throwing it up or whether I'm dropping it, I don't care which direction it's moving in, it has potential energy, okay? So when you're playing rugby or you're playing cricket or soccer, when the ball moves around, that ball has kinetic energy and we don't consider where it's going. If we look at the equation, this equation's a little more complicated, just the math is a little more complicated than with the potential energy one, but it's still not a bad equation. It's actually a really nice equation. EK stands for kinetic energy, and a good way to remember this, and I like to tell my learners as well, the little k is its name. E means energy. So if I say E is like girls, and we have a whole row of girls there, I can't just call all of them girl, because especially in my classes, get a little upset if all you get called is girl, okay? But if one's called Susie, and one's called Mary, and one's called Jane, if I go Jane, Mary, or Susie, you know exactly who I'm talking about. So E tells me it's energy, K tells me it's kinetic energy, it's its name, okay? Same as EP, it's E is energy, P means potential. So it's a good way to remember it. We write them as subscripts as well, which means we write them little, but it is a name. Kinetic energy, just like potential energy, measured in joules. A half is a half, okay, it's a constant. M is mass, measured in kilograms. V is velocity, though often you'll be described, a lot of times they'll describe it as having a speed. It doesn't matter, grade 10s. It's a lot like in the wave section where speed and velocity get interchanged and we use them together. It doesn't really matter. It's squared anyway. So if we are using a velocity which is in the negative direction, it doesn't make a difference because it's v squared. And remember, negative times negative gives me a positive, so it doesn't make that much of a difference. What is velocity measured in? Meters per second. That's important because we are going to try and trick you out because we can. Okay, so kinetic energy, there has to be motion, has to be moving, up, down, sideways, in a circle. It doesn't matter as long as the object is moving. So potential energy is position, kinetic energy is moving. You got that? Brilliant. Let's go to an example. So here we have a car with a mass of 700 kilograms is traveling at a constant velocity. That's going to be quite important here because if his velocity isn't constant, grade 10s, then his kinetic energy is continually changing, and we don't do that at school level. So constant velocity of 100 kilometers per hour. Calculate the kinetic energy of the car. What are we given? Mass equals 700 kilograms. Find mass is in the right units. Velocity is 100 kilometers per hour. Now, I've just said to you, grade 10s, that velocity must be measured in meters per second. We have a problem. This is in kilometers per hour. So what I'm going to do, grade 10s, I'm going to show you how to convert it to meters per second the long way around so you know where I get it from, and then I'm going to show you a shortcut. So this is something you need to tuck in the back of your mind so you all remember. So my velocity, they said to me, was 100 kilometers in 1 hour. Okay, that's what per hour means. We need to convert this to meters per second. So let's think about this and we go, well, if I convert kilometers to meters, I must times by, hope you're all screaming at me, times by 1,000. Because there's 1,000 meters in a kilometer. To convert hours to seconds, hours to minutes, I times the 1 by 60, that gives it into me in minutes. Then I times by 60 again. That gives it to me in seconds. So essentially what I'm doing is I'm going to go 100 times by 1,000 divide by 3,600. Okay, so now watch here. I'm going to go 100 times by 1,000. Okay. Divide by 3,600. Oh, now make sure it's got the 3 there. 3,600. And remember, don't write it as a fraction, 27,78. Okay? 27,78. Grade 10s. In this question, I did not, one of the questions was not show how to convert. Didn't say that at all. Just said, go ahead and calculate, which means you don't have to show this conversion. I want to show it to you because I need you to see how we do it. So that the top I'm converting to meters, at the bottom I'm converting to seconds. How can we do this, the shortcut? Because we all like shortcuts. Well, if I go my velocity is 100 kilometers per hour, the shortcut is to divide by 3,6. Okay, those of you whose maths you really enjoy, you can go and figure that out, but I want you to see something. If I go 100, divide by 3.6, look at that, 27,78. Same value, okay? It doesn't matter as long as we get there. So this is 27,78 meters per second. Do not use the fraction. Do not use the decimal. We don't use fractions in science. We only use the decimals, round it off. I know, and we do understand that by rounding it off, it doesn't make our answers 100% accurate, but we're not always concerned about that. What we're concerned about is the process, and we're concerned that you understand the principle behind it. But we're not done yet because the question was calculate the kinetic energy. All I've done so far is calculate the velocity in meters per second. From the original question, we knew mass was 700. You with me? We want EK, and that's a half mv squared. So we're going to put this into our calculators because it's a half times 700 times 27,78 squared, and I know you can all do this, and this gives us a really big number, which is 270,104,94 joules. You're welcome to put this in scientific notation if you want, but please, I'm begging you, don't use your calculator to do it unless you're really confident. It's a big number, doesn't have a lot of zeros, so I would leave it as it is. We only really want to use scientific notation if we've got lots of zeros either in the front or the back, because when we get a little shaky and we get nervous, we're like, oh, don't know, we get all concerned, we tend to either add in too many zeros or not enough, especially with our long numbers. We want to try and make life a little bit easier for us. But in scientific notation, this is 2,70 times 10, and we're going to move the comma 1, 2, 3, 4, 5 times 10 to the 5 joules. Slightly different answer, both are completely 100% acceptable. Okay, grade 10, so hang in there, not that bad. Okay, so what have we done so far? We've got potential energy, which is a half mv, potential energy, which is mgh, and we have kinetic energy, which is a half mv squared. Okay, that means we now need to look, okay, is we're going to look at, and in the next segment we're going to do this, is what is the relationship, because I've got this potential energy, so it's here, I've got this kinetic energy when it's moving, but there must be a relationship between those two, because if I hold my pen in there, it's got potential. I'll hold it this way. I let it go, now it's got kinetic. Where did the kinetic come from? And if I do it the other way, if I pull my pen up, it's gone from having motion to having potential, or I throw it up. Where's all this going? How's it all gelling together? Okay, and that's our concept of mechanical energy, which is potential and kinetic put together. And on that note, I'm going to give you a quick break, and when you come back, we're going to deal with mechanical energy. So I'll see you in a couple of minutes. Welcome back, grade 10s. I hope you're ready. We're going to go straight into mechanical energy. Now, before the break, we've been speaking about potential, we've spoken about kinetic. Now we're going to put them all together. Now, mechanical energy also is like what we have with potential. It has a special name. It's EM, energy. That's mechanical. That's its name. Now, mechanical energy is defined as the sum, addition, of the gravitational potential energy and the kinetic energy of a system. It's mechanical because it has to do with motion. In the mechanics section, which is what this falls under, we are studying the motion of objects, we're studying how they move, why they move, they do, how they move, the way they do, all of that. So this has to do with the motion of an object. Yes, when we consider my pen again, it has other energy. When it falls through the air, we know there's going to be friction, which causes heat. We're not considering those at the moment. We're simply taking it down to the mechanical energy, which is its potential plus its kinetic. Those two added together, it's the only two we're considering. So when we write this as an equation, because overall we're saying mechanical energy is my potential plus my kinetic, okay, I would write that first, but I can also write it using the two equations I have, knowing that potential is mgh and kinetic is a half mv squared. For both of these, m is the same. M can't change, it's the same object. So this is the mechanical energy for one object or one group of objects that are moving together. You get that? It's not a case of here's my mechanical energy and the potential refers to the pen and the kinetic refers to my hand moving. That's just silly. It's one thing, and we're going to look at how it moves, okay? But why is this mechanical energy so important to us? Because of our conservation laws. You've learned that the conservation of energy as a whole is that energy cannot be created or destroyed. It is merely changed from one form to another. So we know, and you would have done chemical changes in grade 9, for example, we take coal, which has chemical energy in it, chemical potential energy. We burn it in a furnace. That creates heat energy. That heat energy boils water, which creates steam, which is also heat energy. There's lots of heat energy. That high-pressured steam then turns a turbine, so that now creates kinetic energy, which then creates a current in the generator, which is now electrical energy. So we've got all these energy changes. It all still came from the coal when it was after it was mined. Okay, so it all comes from there, and then the electrical energy goes to our homes, and we switch the lights on, so we get light energy. We have the freezer, so we get it's a form of heat energy. Now it's winter a little bit, so in winter we put our heaters on, so it's heat energy. On your TV, it's heat energy and light energy. In your radios, it's sound energy. So we get all these energy conversions, and all starts from the same place. That is what we mean by conservation of energy. But we're not concerned with all those other energies. We're concerned with mechanical energy. So we need to now say, we need this next law, the law of conservation of mechanical energy, that says the total amount of mechanical energy in a closed system, we're ignoring things like friction, remains constant. So if I take an object and we say that at any point in like my pen's motion, it has mechanical energy, the total amount of mechanical energy that it has is the same the whole time. What does that really mean? So, please, grade 10s, we are going to look at some equations, and the way you write this out is really important. This section has been taught for many years, and there's still some people who talk about potential energy at the top equal kinetic energy at the bottom. Don't do that. Please don't, because it's wrong. Okay, so we're not going to do that. How do we write it out? This is the law of conservation of energy. Okay? My mechanical energy at a position 1 could be at the top of its motion, could be at the bottom of its motion, wherever that is equal to the mechanical energy at another point in motion. I'm going to show you an animation in a second, which then means the mechanical energy at any point is potential plus kinetic, which then, and that should have a little 2 by it, we can, and that should be a capital H, let's do, it's close enough, okay? So we can write it out as an equation. Now I'm going to show you an animation which we get from PhET. I'm just going to actually, we're going to reset this. I just want to make it, let's just reset it all. Now what I have here is we have a skateboarder. He's on a skate park. Okay, it's a little exaggerated, but that's okay. And we're going to make an average size. See, I can make him really big, but we don't want to do that. Let's make him small, so he's a little bit more in proportion. And I'm going to show a bar graph. Now, on this bar graph over here, I have 3 things that we're going to look at. Kinetic energy, potential energy. I'm not worried about thermal because at grade 10 level we don't worry about heat. And we're going to look at the total. Now, this total refers to mechanical energy. So that total is my kinetic plus my potential. Okay, and what we're going to do is I'm going to take my little skateboarder, I'm going to put him on the top of it, and then I want you to watch how the graph changes as the skateboarder moves. So, here we go. Okay, now close the bar graph, didn't mean to do that. So here we go, I'm going to take my skateboarder over there, and he's just gone off, let's just let him, and he fell off the end, which is never a good thing. Okay, so let's take him back. I think I need to make him a little heavier because he's not doing so well here and we don't really want him to fall off the end. So there we go, and I'm just going to stop it and take him back over here. That's his starting position. What I want you to notice is potential and total, same value. He's at his maximum height. Maximum height. You ready? Now what we're going to do is we're going to let him go down. Okay, and we're going to stop. I'm just going to do it to there. Not quite where I wanted him, but it's close enough. Now watch what's happened. Potential is pretty much 0. He's already he's already got a little bit of a height, so that doesn't help me very much. My kinetic is now really high. My total hasn't changed. That is really, really, really important. Okay, the total amount of between the potential and the kinetic hasn't changed. Let's look at that. We're going to do it in slow motion. I'm going to let him go up a little bit more, and I'm going to step, but I want you to see something. As I go slowly, and we're going to get to this position right there, it's close enough. Here, once again, the total didn't change. Okay, you can see that that yellow graph's not moving. It's a little hard because of the animation, but at this point, he's about halfway up the slope. So this height is about half the total height. It's about half of that. That's a terrible arrow, but just pretend. So that is about half of the original height. So he's lost half his potential energy. Well, he's going up, so he's actually lost half his kinetic energy, and it's become potential. So what's happened here is, as he's going up the slope, kinetic energy is changing into potential energy. So we're going to play it again, and I want you to realize that as he's going up, I want you to see that the green graph is going to go down. This green graph is getting smaller, and my blue graph, which is the potential, is getting higher. Okay? So if we watch it, we're going to do it slowly. You can see, let's play it. Okay, we do it slowly. You can see quite nicely that the potential is getting higher, the kinetic is getting lower, until he gets to the top. And of course, he wouldn't really be going so slowly, but just pretend. And there he goes. And eventually he will stop. There we go. Now, he's reached the top of his motion. He's got no kinetic energy. So here, EK equals 0 because his velocity equals 0. Potential here is at its maximum. As high as it's going to get. This graph has a little bit of heat in it. We're not worried about that. Heat comes from friction. We're sort of ignoring that it's there. If I now say, fine, let's, ooh, my bar graph disappeared. Let's watch what happens. He's going to go, no, he's turned around. Now he's ready to come down. Now he comes down. I'm going to play it in slow motion, and you can see it as he's coming down. Gets to 0 potential. All his kinetic has come from the potential. So at this point, potential equals 0 because his height equals 0. Okay, so what has happened is all this potential has changed and become kinetic, which means at this bottom point, his velocity is now at a maximum, whatever that might be. You guys are getting this? I can keep doing this. Let's look. This is quite a simple skate park. Let's make a little look at one that's not quite as simple looking, okay? So let's do this one. All I want you to be noticing as we go through this, just like we've done before, is I want you to pay attention to the kinetic, the potential, and the total. Okay, so we're going to put our little skateboarder on. We're going to see what happens. And let's put him over here. We're going to do it in slow motion. And there he goes. Now he gets onto the skate park. Kinetic energy increases, potential. If you go and you look, now doesn't quite get to 0. This is quite an interesting one for you because if we slow it, let's do here, let's get to this point. Okay, now, I want you to see something. He's at a crossroads over here. He was going down, now he's changing direction, he's coming up. I need you to see something here, and it's really, really important. His potential is not 0, grade 10s, because he still has a height above the ground. Only here, at that point, will his potential be 0 because there's no height. That means if I look at the total mechanical energy, it's potential plus kinetic, so it's both added together. This total hasn't changed the whole way through. His potential and kinetic keeps changing, and at this point over here and that point there, the potential will be at a maximum because the skateboarder is now got to its top level. Over here, potential is not at a maximum. It's still my kinetic and my potential, okay, together. But actually what's going to happen here is probably going to be going a little bit slower, so his kinetic will be a bit smaller, but his potential will be higher compared to that point. But I don't need to get to a point where both potential and kinetic are 0. So if we let him carry on, okay, we let him go, you can see, so we look here, let's just step it a little bit. Okay, once again, has potential, has kinetic, total doesn't change. Okay, are we getting how this works? This is really, really important. What I need you to get, and this is what I was saying earlier, some will go like this, that my potential at the top equals my kinetic at the bottom of the motion. I can't say that because that is only valid for this point compared to that point. But if I ask you to compare this point to that point, this here has both potential and kinetic. I can't ignore that. I can't say, well, the potential doesn't exist, because it does exist. So it's very important that you get this, that at the top of its motion over here, potential is at its maximum, but my kinetic is 0. This is so important, grade 10s. At that point, it's the same. At the bottom here, my potential is 0, but my kinetic is a maximum. I know you're sitting there going, but you've said this already. And I go, I know, but it is so important, grade 10s. I cannot actually say it enough. Your mechanical energy is conserved. You cannot say potential at the top equals kinetic energy at the bottom, because we're not always going to give you those situations where you have just a straight top and bottom situation. Also, this is a skateboarder, so it's nice and easy because you can sit on the roller coaster. This works for pendulums. This works for objects dropping. This works for a whole bunch of situations, not just my skateboarder, okay? And let's actually look at a situation where it's not going to go up and down. So we're going to look at one more. So here we go. I want that skate park. There we go. Now can you see there's no up and down here. I'm going to take my skateboarder, put him here. Lots of potential. I'm going to let him go. Now watch what happens. He gets to a point. We've just gone past it where it's half-half. I let him go. Watch. We're going to go slowly. He's going. Potential's going to be 0. And now his kinetic energy. He'll keep going. His kinetic energy is not going to change because now it's at a constant. And once again, we have this. Now, for a situation like this, my potential energy at the top would be equal to my kinetic energy at the bottom, because I have one situation. It's not going anywhere. But I can ask you, what is the kinetic energy, say, halfway? Or how fast is the skater going when he gets to this point, which could be halfway through, it could be at height that's double. I could ask you at this point. It doesn't matter. And this is why we cannot say EP top equals EK bottom. You getting this? I know I'm sounding a little bit like a broken record or a stuck CD, as the case may be, but I need to make sure you get this. Okay, so if we return my skater, shame, he's getting a bit unimpressed with us at the moment. So there he goes, and he goes down, and we see this nice change in, I got that one brilliantly at last. Potential kinetic equal, he's at a certain height, that plus that gives me my mechanical energy, and that total is the same mechanical energy that's over there, the same mechanical that's over there, and in fact the same mechanical energy anywhere on the motion of my object. Okay, in this case it's the skateboard. We getting this? I hope so. So let's go back. Let's just close this quickly. Let's go back to our notes. Here we go. Okay, that's because I'm on that. Okay. This is where it's really important that we understand the situations, because 1 and 2 can be before and after, up or down, doesn't actually make a difference. Okay, so we were looking at a situation where we had a skateboarder, but for example, we could have a pendulum, and this is actually quite a common question, where we'll have a pendulum, child on a swing, it swings through its motion and gets here to the bottom of its motion, and then will swing back up. This height is actually the height that's important. That would be my H. Okay, at the top of its motion, velocity would be 0, so it has 0 kinetic energy, and its potential would be at a maximum at this point, h equals 0, so it has 0 potential. And we can then calculate how fast it's going to be going by the time it gets to the bottom, how high it's going to swing, all depending on the information. Why is this important? Because this is a circle, grade 10s. Okay, that's what a pendulum does, goes up and down like the skateboarder did. You've learned equations of motion, and this is one of those strange situations where using equations of motion would actually work if you had the correct information. So you could solve how fast my object is going using equations of motion, but you will get 0 for it in a test or an exam. Because equations of motion that you learn at school, as we give them to you, are only valid for linear motion. That means motion in a straight line, either vertical or horizontal. Pendulums are circular. That means there is constant change in acceleration because the acceleration has to do with direction. We need to take that into account. At varsity level, you add in that angle. So you do look at rotation and you look at motion in a circle, but not at school level. So be careful, grade 10s, because I have this argument with my learners all the time. You cannot use equations of motion on a pendulum. You have to use conservation of energy. The nice thing is conservation of energy and equations of motion are often interchangeable in a lot of your questions, but the problems we're going to look at after we take the next break is our only conservation of conservation of energy questions, because that's what we're looking at. In a test or an exam, be careful, because your teacher could say, using energy principles, calculate. Then if you use equation of motion, you're going to get 0 because you haven't answered the question. But with a pendulum, we are never going to say use equations using energy principles, because you need to know that there is only one way to solve a pendulum problem or a swing problem or anything like that where we have this nice motion. Like the skateboarder, the only way to solve that problem is using energy principles. You get it? What have we left out in all of these? Last little bit before we take a break. What have we left out? Friction. Not once did I discuss friction with the skateboarder. I haven't discussed air resistance. Friction does play a role in the real world. We all understand that. We can't get away from it. But we take it out of the equation because we want to make your maths easier. I know that just sounds silly, but it is. And I know for some of you really struggle with that because you go, but it's not real. We know that. But we're trying to teach you some principles. In reality, as an object moves, some of its mechanical energy will turn into heat because of friction. But we pretend friction isn't there because we're teaching you a principle. So just stick with it, grade 10s. I know it can be very frustrating, okay? So we're ignoring friction. We don't want to consider it. We're going to add friction in next year, though, when we look at work. So we're going to make your life a little bit more difficult next year. You get in there. All right. Now, I am going to take a short break because a little bit of information overload. When I come back from the break, we're going to look at some problems using conservation of energy and how to actually lay them out so that you can do well on them. All right, so we're going to take a quick break, go get something to drink, and we'll see you in a couple of minutes. Welcome back, grade 10s. I hope you're all excited. I really hope you got your calculators with you because now we're going to get into the nitty-gritty for the last part of the show. So we're going to look at some calculations based on conservation of mechanical energy. Remember, that means the total mechanical energy at the top of its motion of whatever the object is equal to the mechanical energy at the bottom of the object's motion. Whatever that happens to be, a mechanical energy is potential energy plus kinetic. So let's just jump straight in there, and here we have a question which says a bullet of mass, here we go, of 50 grams, nice and small, is shot vertically upwards in the air with a muzzle velocity of 200 meters per second. So what that means is, if I consider this, draw a diagram, it makes it easier. Here's my bullet. It's shot straight up into the air, and its initial velocity is 200 meters per second. And they say, use the principle of conservation of mechanical energy to determine the height that the bullet will reach. Ignore air friction. Now remember that the bullet's going to go up in the air, and then eventually it's going to stop because it slows down, and then it comes back down. They just want to know what is the height that it reaches. What they need you to recognize is that the final velocity will be 0. That's important. So how do we set this out? We're going to go, well, we know that the mechanical energy initially, or at point 1, let's call it initial, is equal to the mechanical energy when it gets to its final position. That mechanical energy means that I'm going to take initial potential plus initial kinetic, which is then equal to final potential plus final kinetic. And I know it feels like we're just repeating ourselves over and over and over again, because we are. So there's nothing we can do. Initial potential means we're going to take mass times gravity times initial height. That will be equal, mass times initial velocity squared is then equal to mass times gravity times final height plus a half mass times final velocity. Now all we have to do is substitute in what we know. But let's backtrack a little bit, because they said to me, my mass is 50 grams. Can we use grams? Of course not. We've got to make it into kilograms. How many grams in a kilogram? There are 1,000. So we're going to take the 50 grams, divide by 1,000. So we divide by 1,000, and it gives me 0.005 kilograms. Please don't forget to do that, grade 10s. I see it all the time, and it breaks my heart. Let's put in what I know now. It's going to get a little hectic because there's lots of stuff for me to write. So what I'm going to do here is I'm going to create a little bit of space for me so that I can actually write it all in without us losing any, so I don't write it in on 2 lines. So I'm going to start it over here. My mass is 0.05. Gravity is 9.8. Initial height was at the bottom, so it's 0. Plus a half. Not 9.8, now I'm lying to you, 0.05. Initial velocity was 200, and that's going to be squared. Equal to mass 0.05, gravity is 9.8, height we don't know, plus a half 0.05 plus 0, because that was my final velocity. So before we even start using our calculator, let's just actually make this a little bit easier to work with. 0, my first one, because I'm going to times by 0, that's going to give me an answer of 0, so I can actually ignore it, which means in my next line I can say that I have a half times 0.05 times 200 squared is equal to 0.05 times 9.8 times HF plus 0, because this last one's also going to be 0. You guys okay with that? So let's actually work that out. So I'm going to do the first part. So I've got 0.5, which is a half, times 0.05 times 200, which gives me 5. Oh, I hope you all saw that. Did you see my mistake? Here we go. That should be squared, and it's 1,000. Wow, that would have been not a good thing to do in your exam. So that's 1,000. Let's see what the next one is. So I've got 0.05 times 9.8. There we go, 0.49 HF. So now to get H on its own, which is actually what we're looking for, I need to take my 1,000 and divide 0.49. Let's do that again. And we get 2040. See, 2040.81 meters. That means, grade 9s, grade 10s, it goes 2 kilometers up in the air. So you shoot a bullet straight up. If we ignore air friction, that bullet will travel for 2 kilometers if it's going at 200 meters per second. Let's do a quick calculation here, and let's just talk about this because I want you to see another trick here quickly. The bullet's going at 200 meters per second. Sometimes it's difficult for you to comprehend what does that mean in terms of real speed, because we talk about kilometers per hour. In the very first part of today's lesson, I said to you that to go from kilometers per hour to meters per second, we divide by 3.6, okay? Which means it's the opposite process for kilometers per hour. So if I want to make this into kilometers per hour, I'm going to times by 3.6. So watch here. What I'm saying to you is that this bullet is traveling at 720 kilometers per hour. Okay? 720. That is extremely fast. Okay? In terms of how long it would take, this will take about 10 and a bit seconds for it to reach its maximum height. That's not long at all. Okay? And it is very high. It's 2 kilometers in the air, grade 10s. I can't even comprehend that. You couldn't see it. But in reality, we also know, though, that the bullet will travel at an arc. It's not going to go directly up. It's actually going to travel at an arc, but we're not worried about that. You guys ready for another one? I hope so. Let's get to the next question. Here we go. A skier of mass 50 kilograms, yay, it's in kilograms, we like it, is at the top of a 6.4 meter ski slope. Determine the maximum velocity that she can reach when she skis to the bottom of the slope. We have to make a very, very important assumption here, and that is that my initial velocity is 0. They haven't said it, but it's the only way we can do this. And what they're saying to you is, here is my skier, and we all know I don't teach art for a reason. She goes down my slope, and by the 6.4, I mean that height is 6.4 meters, the vertical height. I don't care how long that slope is. It's irrelevant because we're ignoring friction. Whether it's like this, straight down, or whether it's a nice, gentle slope, irrelevant. If I was looking at friction, completely different story. But we're not. We're ignoring friction. And it's a skier, so we're assuming it's snow. Snow is nice and slippery, very little friction. So what do we know? We know at the top, velocity is 0, and we want to know what is the velocity when she gets to the bottom. We know height. So we go, we can do this. Of course we can. So let's do this. Mechanical energy at initially is equal to her mechanical energy finally, which means her initial potential plus her initial kinetic is equal to her final potential plus her final kinetic. And yes, we're doing the same thing over and over again. And we're okay with that. Remember, grade 10s, practice makes perfect. When it comes to mechanics and it comes to physics, I cannot tell you enough how important it is to practice, practice, practice. So, potential energy is a mgh, that's my initial height, plus my initial velocity squared is now equal to my final plus my final squared. Alrighty, so we know her mass is 50, gravity is 9.8. They said the slope was 6.4 meters high. This is 50. Initial velocity is 0. And we get to the bottom, so now we can say, well, that means my final height is 0. And that's 50. And we're now going to have to calculate VF squared. The only thing I really don't like about this is that it's velocity squared, so it makes the math a little tricky, but we're okay. you guys can handle it. So let's calculate this first part where we have 15 times 9.8 times 6.4, and we get 3,136. So this is 3,136 plus 0. You don't have to put it in, but we're going to add it in for completeness. That's also 0. And I'm hoping we can all go half times 50 is 25. Okay, 25. Let's do VF squared. So that means 3,136 is equal to 25 VF squared. To get VF squared on its own, we're going to divide both sides by 25. And I didn't mean to do that. Let's go here. So 3136 divided by 25. We get 125,44. Please be careful here, grade 10, because I know exactly what happens after this point. You go, there's my answer. No, sorry. This is VF squared. So we need to remember we want velocity on its own. So we need to square root. I'm just going to put it here in white. We need to remember that we're going to need to square root both sides. So that means we'd put another line that says that VF equals. Don't just say equals. So a lot of times you do this. I'm going to put it on the side here. You go 125,44, and you go, yes, 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 I know I need to find it. And you find an answer, but you forget to tell me that you've square rooted it. So now you're telling me VF squared equals 125. This is going to come down to about, I think it's going to come down to, I actually don't know, it's going to come down to 11 something. So you then give me an answer here of 11, whatever it is. And now you're telling me that VF squared answer is equal to two things, 125 and 11. How is that possible? It's not. So mathematically, very, very wrong. Make sure you write VF, okay? So I'm going to need to square root that. If you look at your calculators, it's actually really nice because I can go square root answer, which is the answer from the last question that I had, and it gives me 11,2. So that means it's going to go at 11. She's going to go at 11,2 meters per second when she gets to the end. Let's put this in context. It's times by 3.6, which means she's traveling. Oh, no, I didn't mean to do that. There we go. At 40 kilometers per hour. Personally, I would not want to be skiing at 40 kilometers per hour, but that's just me because I'm a little bit of a baby when it comes to things like that, okay? 40 kilometers per hour, that's quite fast, but it is quite high, 6,4 meters. That's a couple of more than a couple of stories. It's actually relatively high in terms of a vertical drop. Now, next question. Do you think she will reach this velocity, which we've just worked out to be 11,2 meters per second? Okay, that's what we've worked it out to be. Do you think? I'm hoping you're screaming at the TV at this point, going, no, no, she won't. And you would be correct. Of course she won't. But why? It's an unusual way to ask the question. The question would be explain. Why will she not? So no. The answer to the question is no. Why? We have ignored friction. This is so important. Friction will slow her down. Okay? So friction slows her down. And what will happen is some of the mechanical energy will be converted to heat. Okay, so some of that potential she has right at the top of that motion is converted to heat as she travels down. This happens with any object that's falling. Like I said right at the beginning, we ignore friction because we're trying to make it simpler for you. Grade 11 and 12, when we do work, when we actually look at what's happening in a little bit more detail, we will add friction in. Then we're going to have some fun with the calculations. But for now, we ignore them. In reality, she will not be going that fast. which is probably a good thing. We're quite grateful that there's friction. If she was skateboarding, the friction would be more because she would be on a road or another surface which would be quite rough in compared to snow or ice or something like that, which is considered almost frictionless. But the whole point here is we've ignored friction. Friction will slow her down because friction creates heat. That heat takes away from my conversion to kinetic energy. Okay? You ready for another one? I hope so. So here we go. A man fires a rock out of a slingshot directly upwards. Out of a slingshot directly upwards. That's not directly upwards. So directly upwards. Has an initial velocity of 15. And they want maximum height. So let's look at this. We want final height. We know initial height would be 0 because that's where it starts from. Final velocity, this is the same concept as the bullet, where final velocity is going right to the top, final velocity is 0, and initial velocity is 15. And we have a problem. Are you looking at this going, hang on, wait, stop the bus, Tracy. There is an issue. I don't know maths. Okay. Now, grade 10s, I know what happens at this point is you look at this question and you go, okay, don't know maths, can't do it, I'm stuck, I'm just going to wait for my teachers to do it. Don't ever do that, grade 10s. Don't ever say, no, left out information, can't do it, because actually you can do it. Work through it with me and I want to show you. This is exactly what you do. We've made a list and we go, small problem, I'm realizing there's an issue. Okay, we know there's an issue, but let's work through it. Let's see how far we can go without knowing the mass before we give up, before we go, okay, not a problem. Let's see. So, mechanical energy initially is equal to my mechanical energy afterwards, so when it gets shot up. So that means my potential initially plus my kinetic initially is equal to my potential final plus my kinetic final. Okay, now we know we're going to start running into problems, maybe. So my initial height plus my initial kinetic, so I'm using my initial velocity squared, is equal to my mass times gravity times final height plus mass. Okay. These first three lines, first of all, grade 10s, they should be ingrained in your head, automatically written down. I know it feels a little bit like we're repeating ourselves, and we are, but we're showing the science. And remember, grade 10s, the process, how we get to my answer, is far more important than the answer itself. That's what we're looking at, is do you understand the principle? Which I'm hoping you're getting. So, let's put in what we know. I don't know the mass. I know that gravity is 9,8, and I know that my initial height is 0. I don't know mass, but I know that the initial velocity is 15. Don't know mass again, 9,8, and I want final height. I don't know mass, but I know final velocity is 0. Okay, now we know, because we don't need our calculators, for this mass times 9,8 times 0 is going to be 0. Plus, now I'm going to do 15 squared because I can do that, times by my half, and I get 112,5 times m, I'm leaving the m, is equal to 9,8 times m times final velocity. I'm just rearranging this last one over here, this one, grade 10s, because it's going to make it a bit easier later on, and it doesn't matter with multiplication which way around you put them. Now, a half times mass times 0 all squared is 0. Okay, we're now going, alrighty, I still don't know M. I have a, no, don't give up yet. 112,5 times M equals 99,8 times M times HF. To get that final height on its own, we would take everything that's been multiplied by the final height, and that's what we're going to divide by. So I'm going to divide by 9,8 M on that side, 9,8 M on this side. So 9,8, 9,8, M and M. Oh wait, look at that. What happened to your M's, grade 10s? They've gone. Do not give up because they didn't give you a piece of information. It is deliberate, okay? So don't just give up because you couldn't see it. And trust me, grade 10s, I know grade 12s who would do the same. I put this question in deliberately, so I wanted you to see this, because actually what I'm saying to you is my final height is 112,5 divided by 9,8, and if we do this on my calculator, divided by 9,8, we get 11,47 or 5. I didn't need to know the mass at all, which actually makes life really, really nice for us. We don't have enough information to calculate the mass. That we definitely don't have. So nowhere with what I've got here can I calculate the mass, because remember, I could also go the other way around. In all these questions, I haven't actually asked you to calculate mass or anything like that by giving you the energy. We haven't given that information. I can't actually calculate. Okay? Now, little bit of an extension to this question. It says to us, same question, man fires a rock. And he says, now they say draw graphs, they will be sketch graphs because I don't have enough information to show how the potential energy, kinetic energy, and mechanical energy of the rock changes as it moves to its highest point. Draw graphs. 3 graphs. Potential energy, kinetic energy, total mechanical energy. Now, on the animation I showed you, we were using a bar graph, but it was nice because you could see it move. That's not what we want. Okay, in science we never use bar graphs to find information. So let's do some axes. So here we go, and we're going to do 3 graphs. So I'm going to draw 3 sets of axes, and what we're going to do is we're going to quickly what I want to do is I want to do that one with, okay, hang on, wait. I'm going to put these together, I'm going to make it into a group, and I'm going to quickly copy them so that I don't have to draw them again, because I'll never get them to all look the same. So here's my 3 graphs. Let's just put that one over there, and we're going to put, there we go, and there we go. Okay, so 3 sets of axes. We're now going to work on them. First graph I had to ask was the potential energy. As it's moving, so now we're going to go, well, I know this is going to be potential energy, so I'll write that as my label, because that's what I was measuring, and it's measured in joules. Don't forget its units. But now, what's going to go along this axis? We're going to, well, we're looking at its motion, so we're going to compare it to time. Okay, and this would be in seconds. Now, the potential energy changes over time, and it gets smaller, and it's nice and linear. Let's draw the graph of potential energy. Remember, we start from 0 potential because it's been thrown up, not down. Okay, so it's been shot upwards, and as it goes up, its potential is going to increase, but it increases uniformly. So what that graph is actually going to look like is it starts at 0 and it's a straight line going up, okay, because it gets to its maximum potential at the top of its motion. Let's now look at the kinetic energy. Now I've already written it in, and because potential, we went time across the potential, or potential versus time, we need to do kinetic versus time. Okay, we can't change that. Now we need to think about this one and go, well, the rock was slingshotted at an initial velocity, so it started with an initial velocity, which means it's got kinetic energy. As it moves up in its motion, it gets slower and slower and slower until it stops, which means its kinetic energy becomes zero. But potential and kinetic energy must change at the same rate because their total remains constant. So what happens here is your kinetic energy is also a straight line, but it starts at a maximum and becomes zero. Okay? That leaves us with the last graph. So here we have our axes. So, I was getting all excited. There's my axes. Okay. Now, what we're going to do here is we need to do the axes. So let's label it. This is total. So this is mechanical energy. Also in joules. This is time. And we remember that the total stays constant, so it's a straight line. Simple as that. Nothing overly difficult with those. Those are a little bit of extension though. So, grade 10s, what have we covered? Potential energy is the energy of an object due to its position in a field. Gravitational potential energy due to its position in a gravitational field, where potential energy is mass times gravity times height, gravitational acceleration. Kinetic energy is the energy an object has due to its motion, and that is equal to 1/2 times mass times velocity squared. Energy being a scalar, we don't care about direction. Mechanical energy is the sum of an object's potential and its kinetic added together. Okay, so we add them together. It's also a scalar, and it's about its motion. Conservation of mechanical energy says to us that the total mechanical energy of a system remains constant if the system is isolated. So the total mechanical energy at one point equals the mechanical energy at another. Potential plus kinetic equals potential plus kinetic. Okay? Wow, grade 10s. We have done a lot of work. We've gone through some really good problems. The best way to get this into your head is practice, practice, practice. And don't forget units and don't forget zeros when you need to add them in. Okay? So we're going to actually end it there for today. I really hope you found this useful. I really hope you managed to learn a lot. Good revision. And we will see you next time.